Welcome back to another tutorial. Today we are going to recreate Color Break by Lucas M. This is a game where you control a ball as you bounce around a level breaking blocks of the same color. There are different types of blocks. There are those that you destroy, and there are those that destroy you. There are those that change your color, and there are those that slide to your order. This game drew its inspiration from Quillian, an arcade game released in 1988 for the Commodore 64, wherein you have to complete levels filled with breaking blocks with only a limited number of lives. In this video, we are going to replicate this game along with all of its mechanics. Now, let's begin. Before we start, I went ahead and created all of the blocks we'll need for the game to save time. As you can see, we can have 5 different colors. These are the balls that our player will control. We also have our normal breakable blocks, this star block to represent the color changers, and this exclamation point looking block to represent the pushables. We also have this danger block and a wall block to construct the level. Take note that all of these blocks are glued in all sides to avoid sticking to one another, with the wall block being the only exception. The first thing we have to do is to assign all of these blocks their corresponding colors and types. To do that, we would need to create a module. This script block will need 3 inputs: the object itself, a number representing the block's color, and a number denoting the block's type. Bring a play sensor to have it run once at the start, then utilize list to keep track of a block's properties. Then, update the list length and rename the wires. After that, let's talk about the IDs we'll use to signify the color and type of the block. For the colors, we start with 0 for red, 1 for blue, 2 for yellow, 3 for green, and 4 for purple. For the types, we have 0 for the normal block, 1 for the changer block, and 2 for the slider block. We'll also add this module to the skull block with 3 as its type. Also, the reason why we opted to keep all of these blocks within a single list despite having different purposes is because when we start to implement the player collision later, we would want to get the block the ball collides with. Therefore, it would be more efficient to have a single loop encompassing all of the blocks rather than running multiple loops, one for each type. If we do find a matching block, all we need to do is to inspect its type, then we branch out to more specific actions based on the value. Now that we got that out of the way, let's start attaching this module to all of the blocks. Once we're done setting up the boxes, let's create a simple level to test out our game. The first thing we have to do is to figure out the edge coordinates to help us position our camera in the middle. In theory, we could just have a get size block to do that, but I would want to use this moment to have a quick refresher about snapping positions. So, bring out a script block to represent the bottom left corner, then on play, get its position, break the vector, round out all of the coordinates, combine them back into a vector, and add an offset of 0.5 in all axes. Let's name our variable SW, our southwest coordinate. Then, let's duplicate this code before creating another script block for the top right corner. Grab our code and place it inside and rename the variable to NE, our northeast coordinate. Next, position our script blocks at the edges of our level. With that being said, surely I won't forget that these variables ever existed for the rest of this tutorial. This is called foreshadowing. Now, we also need a way to position our ball in the level. This time, we can't actually use a script block. Well, we can, but we just won't be able to hide it during playtesting and that can be annoying. Instead, let's just bring a marker and edit it. Inside, we get its position and save it to ball, the ball's position, before hiding it. Then, let's create a script block to contain all of our code. From here, we'll initialize all our colored orbs and store them in a list. Let's also make use of comments to give context to our chunks of code. Then, let's bring out a new variable to be the ball's color and attach the wire outside of the script block. This is so that we can modify its value if we ever want to start with a different color, because by default, it is just going to be red. Next, let's reveal the ball with a corresponding color and assign it to be the ball with a $sign. While we're at it, we might as well customize the variables we'll need for the movement later. Set the play speed at 0.125 and the direction at -1 to go down. Next, we need to determine the number of blocks we have to break within the level, as that is the main objective of the game after all. So, loop to the blocks and check if its type is equal to 0, as that is the index for a normal block. It's also fine to just leave the second wire unattached because that will just default to 0. If this is true, then re-increment the new variable goal. Let's inspect this value and count the number of boxes in the level. We have 5 blocks, therefore we should have a value of 5. If we press play, we can see that we're correct. Afterwards, let's set up the camera. On play, we take our edge cord. Oh my god. I did actually forget the edges. I am so sorry. But at the same time, it is kind of funny that I brought something up only to never use it for the rest of this tutorial. Just imagine that this getSize block is our vector variables. Then attach our cam variables to a set camera block. Have our rotation be 90 in the x-axis to get a top-down view. Then play around with the light rotation and control the shadows in the level. Next, let's update the ball's position using our vector variable. Now, we don't want to start a game as soon as the player boots up the level. We need to give them some time to simmer down and prepare before the game begins. That is why we are going to add a delay to that. By delay, I mostly mean a timer. The idea is to have some variable that counts up every frame, and once it reaches a certain number, we tell the game to do something. Create an if condition that checks if the ball has started moving. Obviously, it would be initially false, so connect it to another if block that checks if a variable is greater than 30. We'll call this variable empty. If this is false, then re-increment its value. This allows the game to wait for 30 frames. Once true, we also set the boolean to true and add a marimba as effects. When we press play, our ball is in the level and after a short while, we hear a noise. Next, let's set up the ball's vertical direction using our variables earlier. Bring out a vector with 1 in the x-axis to signify the up direction before attaching it to a scale block. This block multiplies each vector component with a given number. Say we have this random vector and we want to scale it by 3. By plugging them into a scale block, we carry that number and apply it to all 3 coordinates. In our case, only our z position has a non-zero value, so as expected, scaling this vector only affects the z value since we would just be multiplying by 0 for the other 2. Let's have our magnitude be the product of the direction and speed variables. Then, let's set up our controls. We begin by implementing a logic gate to toggle the controls. We would want the game to have started and to have not stopped. Combine them together with an end block before plugging it into our boolean. We then create an if condition checking for its value. If this is true, then that means the player can move the ball sideways. Similar to our direction variable, we'll also use a number to signify our horizontal movement. The key is to add buttons to control the variable's value, so let's talk about it. This block builds a button and brings it at the bottom of the screen. When a button is pressed, it sends out a signal that you can use to execute some code. You can have up to 4 buttons on your screen, or up to 2 if you also have a joystick equipped. A button can have 2 visual modes. Button, which displays a circular ring, and direction, which displays an arrow. If there's only 1 button, then this arrow points up. If there's 2, then they point left and right respectively. If there's 3, then they point left, right, and up respectively. And if there's 4, then they point left, right, up, and down respectively. We'll keep it to be a direction as we are moving left and right. The first button is at the left side, so we should decrease the variable if pressed. The reason why we don't just set it to -1 is so that in situations where the player is holding both buttons, we could lock the ball in place instead of picking some direction. For the second button, we increase the value. Let's also add a boolean that returns true if the side variable holds a value. We'll also update the ball's position by adding it with our direction. When we test this, the ball goes down. Going back to where we manage our direction, we'll update this to implement our horizontal movement. This time, we set our x-axis to have a value of 1 before scaling it with our side direction multiplied by speed. When we press play, we can slide our sphere sideways with our buttons. And if we change the direction to be 1, our ball moves upwards. Next, let's sort out our collision. The idea is to have a set of 3 raycasts projecting from the ball based on the current vertical direction. If the play is moving to the side, then we'll also add another set of raycasts based on where it's going towards. It's important for these two groups to not have any intersection to avoid unnecessary changing of directions. Have a loop that runs 3 times, subtract the index by 1 to get the values -1, 0, and 1, then make a rotation for angling the raycast wherein we multiply our index by 30. For the actual rotation, aka if it should go up or down, create another rotation wherein we take our direction variable and find a minimum value between that and 0 before multiplying it by 180. So if the direction is -1, then it rotates by 180 degrees and points down. If the direction is 1, then the min block takes the lower value which is 0 and we don't do anything to the rotation, which is what we wanted anyway. We combine that rotation with our angle. For the raycast and position, we stem from the ball's position and add an offset of 0.375 in the z-axis and rotate it. Then we set up a raycast with the ball position as the starting point and our variable as the goal point. Let me just quickly fix this, and we got it working. If we change the direction to go up, notice how the raycasts adapt and also point up. If any of the raycasts hit something, then we retrieve its hit position and object. We also negate the direction to have the ball go the other way. When we press play, our ball bounces back and forth, though we still got work to do. If this holding boolean is true, then we'll also cast some rays to the side. Copy this part of the code and replace this number with 90 before attaching the side variable. If the variable is -1, then this becomes -90 and looks at its left. If it's 1, then this becomes 90 and looks at its right. We will also duplicate this code and attach it here. If a collision happens, then let's introduce a new variable bump and set it to 3. This number acts as both a way to invert the horizontal direction as well as a delay. Basically, as long as this number is greater than 0, then we do something with it, while also decreasing its value. Let's update our direction. Subtract our variable by 0.5, get the minimum value between it and 0.5, negate it, multiply by 2, and scale it with our side variable. If we test this out, we can see that our ball now bounces off at its sides. What's happening here is that, if bump is equal to 0, then it becomes -0.5, which we then use as a lower value before it gets negated to 0.5, which is then multiplied by 2 to become 1. So if it's 0, then we essentially leave our side variable unchanged, as we are just scaling it by 1. If it's any greater, however, then we take 0.5 as our lower value, negate it, and multiply by 2 to get -1, thus allowing us to invert the side direction. Once we have our hit object, let's set a boolean to false and loop to the block list to find our match. At the end of the loop, check if this is still false. If so, then play some SFX. To look for a block, we need to check if these two objects have the same ID. If this is true, then let's store the block type to a variable and have the boolean that checks if the block's color and the ball color are the same. Let's first take care of the normal blocks. Have an if condition that checks if they have the same color and if the type is equal to 0. If so, then we set the boolean to true, hide the object, decrease the goal number, and play a hit SFX. Let's inspect the goal variable before testing, and as you can see, that number goes down every time we break one of the blocks. We could also add some particles to give a little bit more pop to our game. Even though the block is hidden, it is still technically present in the level, so we could use this object as a point of reference. We'll spawn a random amount of particles and sprinkle them somewhere within the vicinity. We'll also influence them towards a random direction to disperse. After a short amount of time, they all disappear. Let's store our hit object to a placeholder variable. Then loop for a random number of times. For me, I'll just set it between 2 to 6. Inside this loop, we create a copy of the particle and insert them into a list. For the position, we take our placeholder's position and add an offset with a randomized x and z value. For the direction, we'll use a vector with some value in the z-axis, representing the speed, and rotate it with some random y value between 0 to 360. Then, finish it off with a list length increment. Next, let's loop to the particle list to update them. First, we check if the object still exists. If it does, then we move its position based on the particle's direction. If we press play, you can see our particles spawning and moving away from their starting locations. Then, we'll implement a lifespan to our particles, so that they dissipate after a while. And let's specify that number to be 15 frames. We'll keep increasing its value until it's greater than a number, before destroying the object. Let's check if it works, and it does! Our particles cease to exist once they reach their expiration date. The next type of block we'll implement is the danger block. Let's quickly design a small level featuring those skull boxes. I'm also going to use a different color to test if our input wire by the script block actually works. Let's set it to 1 as this pertains to blue, and it works. Let's also swiftly go through each color just to make sure. Now we can break the normal blocks. Sweet! However, we don't want to touch those danger boxes as that will make us lose. But we still need to code that, so let's bring in another if condition that checks if the type is equal to 3. If this is true, then we hide the ball itself, assign it to our object variable, set the stop variable to true to disable the controls, attach a loose block adjusting the delay, complement it with a fitting noise before attaching it to our particle script. If we test this out, we can see that our ball goes kaput as soon as it touches one of the danger blocks. We should probably lower the volume though. The next in our list are the changer blocks. Mock up a level that showcases this type of block. Press play and we have a yellow ball, therefore we can break the yellow block. However, we can't do the same for the green block as we don't have the same color. That is the job of a little asterisk in the corner. Have an if condition checking if the type is equal to 1 and if the colors are different. If so, then we hide the current ball, update the ball color, reveal the corresponding ball, assign it to be the player, and position it in place. Let's also add some splash onto it. Now we can switch the ball's color from yellow to green, allowing us to remove the final block in the level. The last type of block we'll add to the game is the pushable block. Once again, I'm going to construct a level highlighting this particular mechanic. When we press play, we can see that our ball is trapped. The plan is, whenever the ball comes in contact with the block, we check which direction the player intends to push the box to. Then we draw a line to check if there is anything blocking the way. If there isn't, then we move the block there. Let's see if the block's type is equal to 2 and if they share the same color. If true, we get the hit object's position and subtract it with a hit position, giving us the offset between the ball contact point and the actual object's position. We then attach it to a look rotation to convert the vector into a rotation before breaking it. Now, to have a rotation pointing to a cardinal direction, its y value should be a multiple of 90. However, unless you've collided with a block with perfect precision, there is a good chance that you won't get one of those values. So, what do? Well, we'll just need to round that number to the nearest multiple. To do so, we divide our y value with our chosen number, in this case 90, round it, and multiply it again with the number. Think of it as a slider with 4 different points as we assign them the numbers 0 to 3. Let's say our slider is between these two values, then move it to be a little bit closer to 90. Dividing this value will give us a number between 0 and 1. Rounding it allows us to confirm that it gravitates towards the second point, and multiplying it back gives us 90. With that being said, let's place them blocks. After that, set up a raycast starting from the object's position, and add an offset making use of rotation. For the vector, let's set a z position 1 to travel a full block. While we're at it, let's quickly add some comments. If that gives us something, then we would want to keep the object inside a separate list to specifically deal with our pushable blocks. For the direction, it is important to set the vector to point to, though I'll elaborate more on this later. We also told the game that this particular block is being pushed, in which we'll also append to our if condition here. The reason being, we don't want to push a block that is currently being pushed. We also need a way to keep track of the block's ID so that we can reset this boolean later. Update the length and add another sound. I also forgot to set the truth variable to true earlier so that we don't run that SFX by the end, though it's not really that big of a deal. Create a loop for the pushables. Set up a little timer that counts up until that number reaches 4. This will run 5 times as we start from 0. That is why we have specified our offset to be 0.2, so after the timer ends, the box would have moved by 1 unit. Let's update the block's position using our push direction. Once the timer is done though, check if some boolean is false and turn it to true afterwards to only run it once. Then set our block push property back to false using the ID earlier. Let me just rename this. And now, we can push the slider and make way for our ball to the box. Finally, let's create our win condition. While the controls are active, check if the goal number has reached 0. For now, let's plug it to an SFX block for testing purposes. As expected, we hear a noise once there are no more boxes. Afterwards, let's set up a delay for 20 frames. Once that's over, we stop the game and connect it to a win block. Let's see if this works. And there we have it. Also, the reason why we added a delay is because there is a chance the player hits a danger block while waiting for the win, and since the game is still technically active, they are very much prone to losing. We have now concluded our game making process. Now it's time for you to take matters into your own hands and create your puzzling levels. This seems a little bit zoomed out. Man, I wonder why that's the case. So I'm just going to decrease this by a bit. But anyways, that's all the time we have left for this tutorial. I hope you learned some new things that you can implement to your own games. As always, there is a GitHub link below that shows all of the code screenshots, as well as a glossary for all the variables we've used throughout the video. Thank you for watching, I'll see you at the next one.